Welcome back to our video module on statics. Now in our last module, we took a look at vectors. And we used a barge example where we had two tugboats, tugboat A and tugboat B. And we kind of felt our way through what was happening in the X and the Y direction. But one of the things we did right off the bat is we took these vectors, and vectors are big, powerful concepts that can do all sorts of great work for us. We took these great concepts of, vector A going in this direction and vector B going down in that direction. We took them and right off the bat, we killed them. We put them into the sum of the forces in the Y direction and the sum of the forces in the X direction. I'd like to explore today what happens if we didn't kill him. What happens if we tried doing this entire problem and we kept all of our vectors? We didn't put it in X and Y components. We simply kept everything as vectors. Let's take a look at how we can navigate this problem, and I think we'll see how powerful vectors can be. Let's go ahead and copy. Let's see, I copied this problem here. We did our row reduction. We ended up, just a reminder, remember all that algebra. I mean, look at substitution. We blazed through it. It just took us some time, and that's a natural, easy way to do these simultaneous equations. We also did row reduction, and that looked a lot better. But it's not hard to imagine that you add, 3 by 3, and suddenly things get a little trickier. All right, so in this case, let's try exploring this. Let's think about what would happen. We're going to take our sum. Let's stick with white. We're going to take a sum of our forces, but now our forces are going to be vectors. That also means that if we're going to do that, that our acceleration, our movement has to be vectors. Now the good news is, in whether or not we use vectors or scalars, the acceleration, there isn't any. This is the wonderful part of statics. A lot of the mass times acceleration, we just let it go. Now, that said, let's take a look at what vectors we have. First, let's take a look at force of A. So this is basically vector A. All right, so in the top term, we're going to have, our X. We're going to put our X in the top and our Y in the bottom. And it's sine 30 times the magnitude of force A. And in the bottom, let's make sure we keep everything right. On the bottom is going to be sine of 30 times the magnitude of force A. Now, this gets really cumbersome. We generally don't do it. And so what we do, combining force of A with, a coefficient, we use our unit vector. So our unit vector has a magnitude of 1 going in the direction of force of A. That way we can say the unit vector times the magnitude of force A, this is going to be force A. Well, so what that ends up being, if we really want to parse that out, is sine of 30. Cosine of 30 and sine of 30 on the second row times the magnitude of force A. So here's our vector, and we're going to need to use matrices. We're going to pull those in to be our friends because they're gonna really help us out. Well, let's take a look. Force B, we follow the same protocol horizontally or in the X direction, in the I, if you look at it that way, is going to be cosine of 45. Now this is important. It's in the negative Y direction, so we're sine of 45 times force B. Remember, in the top row is here we go. In the top row, we always put our X components. And in the bottom row, we put our Y components. Or, another way to say it is I and J. We can use both of those. I and J is probably more appropriate over here. Regardless, let's also put in, because we're doing all vectors, we also need to do the force of drag. We know what this is in the top, in the X direction. It's 10,000 in the negative direction. So it's negative 10,000. In the Y direction, 0. We got nothing. All right. So here, we have our 3 vectors. And let's go ahead and sum them and see what we have. Sum of the forces is is FA plus FB plus FD. Okay. Now, I know what's going to happen. I know that I like variables being on one side and numbers being on the other. So I'm gonna go ahead and move vector D over to the other side. We'll rewrite this equation as force A plus force B. Now at this point, we're making those forces really powerful, but the equation is unbelievably simple. You know, I mean, I could give this to my, my 6th grade daughter, and she'd be like, oh yeah, you just add them together. That looks pretty simple. It's just that we're using matrices now. Now, if we get to this step, we already know where we're going to fall back. We're going to fall back on what we know about when we add vectors. When we add vectors, and you can look right here. This is us adding, A is the white vector, yellow is the B vector. So let's go ahead, and if you haven't done it before, by all means, make sure this makes a lot, revisit this and learn this. Well, we know precisely what we're going to have here. We're going to have, for force of A, we're going to have the cosine of 30, sine of 30. Force B, cosine of 45. Remember the sign here. Negative sine of 45. Remember, it's going in the down direction. And that's going to be multiplied by force B. And let's keep those colors. Force A. And remember, we moved that 10,000 to the other side of the equation. It's a, we got a double negative there. 10,000, 0. Now at this point, we have a really easy equation. I mean, honestly, this is not that different than, something I might give my 6th grade daughter. 2x equals 4. Here's your number. Here's your variable. Here's the other number. And what do? We multiply both sides by a half. So we're going to multiply both sides by the inverse of this matrix right here. We're going to multiply both sides by the inverse of this. Well, that's going to leave, on our left-hand side, that's going to leave the identity matrix. And on our right-hand side, that's basically going to look like this. We know how this works. We've seen it before. Force A, force B. Let's call this matrix right here, let's call it C, for lack of a better. All right, that's going to be the inverse of C times 10,000. Now, back in the day, I remember having to always do these by hand. We never had calculators that could do this. So if you're taking this now and you're in high school or you're in college, live it up. Live the dream right now, because it's absolutely fantastic. You run this into your, whatever you have to help you out, and you'll find that force A is 7,320. Force B is 5,177. Now, all that said, let's review what happened here. I started off on the first problem doing things in X and Y. And we ended up with this giant thing of algebra. And I suggested, well, let's try row reduction, simultaneous equations. That's going to make things a little easier. And of course it did. But now what I'm saying is, let's keep these vectors. And we know, I really took my time developing what those vectors are, but they're all going to look the same, which means that when it comes time to solve this, we can jump directly to right here. Well, maybe putting the numbers, isolating the numbers is a little bit premature. Maybe we really should start off summing the forces. Whoops, I didn't say they were equal to 0. Setting them equal to 0, and then from there we go right to here. The good news about this is, if we have 3x3 matrix, or I don't know, 4x4, I guess we really won't see that, but in dynamics you might see 3x3, and you'll see that in statics as well. No matter how complicated we make this problem, it's one equation. It's simply one equation. We plug through and we use the power of the matrices. So I wanted to cover what it looks like if we really did the problem with vectors rather than just putting them into their x and y terms right off the bat. If you're a little shaky on this, take some time to develop matrices, your matrix algebra, develop your vectors until you're more and more comfortable, because the time is coming in dynamics where you'll need to be comfortable in this. And the sooner you start, the easier your later studies will be. Nothing wrong with doing substitution, row reduction, that's fine. But go ahead and basically include vectors in your toolkit more and more. Thanks, and we'll see you soon.